Good afternoon. I hope you can hear me. Okay. So first, I would like to thank the organizers for inviting me and giving me the opportunity to present you this talk today, for organizing this very nice venue. So my name is Michael Stern. I'm from the Quantum Nanoelectronics Laboratory of Bar-Ilan University. And so the Quantum Nanoelectronics Laboratory belongs to two centers at Bar-Ilan University. First, the Quest Center for Quantum Entanglement, and the second, the BINA Center for Nanotechnology. And well, what we want to do is to, in fact, connect two different worlds. On one hand, you have the world of superconducting circuits, which are very easy to handle. On the other hand, you have the world of spin in semiconductors, which can keep quantum information for very long times, can store safely quantum information. And we would like to take the best of the two worlds. And in order to do the best of the two worlds, and in order to do that, we need some element, and the element that we want to use to do that is a superconducting flux qubit. So by doing so, we would be able to couple to several spins. So we would have clusters of spins, and then be able to connect several superconducting flux qubits by that way, and therefore connecting several quantum units. And what I'm going to speak today is about the reproducibility and control of superconducting flux qubits, this element. Okay, so the tool for connecting these two worlds. So I'm going to make you a very small introduction about superconducting qubits. Then I'm going to, speak about our last results about flux qubit with long and reproducible coherence time. And I'm going to try to show you the perspectives that this opens us. So when one speaks about quantum harmonic oscillator, I think that everybody has in mind this kind of spring with 2 degrees of freedom, the position of the spring and the momentum of the mass. And since x and p do not commute, we can solve the Schrödinger equation. And at the end, what we get is energy levels which are equally spaced and separated by a distance which is fixed by h bar omega, where omega is square root of k over m. And well, in fact, we can do exactly the same with circuits by just considering this LC circuit. So when L is playing the role of the spring, the capacitor is playing the role of the mass. So the charge on the capacitor is playing the role of the momentum, if you want, and the flux threading the inductance is playing the role of X, the potential. And indeed, we have exactly the same kind of commutation relation between the phase and the charge. And the frequency will go like 1 over square root of LC, so it should behave quantum mechanically. So when does this behave quantum mechanically? Well, you need for that to have 2 conditions. The first condition, you need to have a temperature which is much smaller than the distance between the levels. The second thing is that you need that the level width will be small in front of the distance between the levels. So this requires to have high quality factor. And indeed, when working with the superconducting circuits at 20 millikelvin temperature, this fulfills these 2 conditions, and thus we can have a quantum harmonic oscillator based on a circuit. But these circuits, they have another advantage in front of a spring, is that we have a wonder of nature, and this wonder of nature is a Josephson junction. The Josephson junction is at the same time a nonlinear and non-dissipative inductor. So you have a lot of elements in nature which are nonlinear, but in general they are dissipative. You have a lot of elements which are dissipative, but in general non-dissipative, but in general they are linear. So the Josephson junction is a sandwich between a superconductor insulating a superconductor, and this is the same micrograph showing you a typical aluminium oxide, aluminium Josephson junction. And indeed, when we write the Hamiltonian of this junction, we have, rather than having a linear or quadratic, if you prefer, potential, we have a cosinus potential, which will give you an anharmonicity in the potential, and thus will give you access to consider a manifold formed by the two lowest states, which we will consider as a qubit. So a good example of such a qubit is the so-called Transmount qubit. Here you see a microscope picture of a Transmount qubit, which is made out of an interdigitated capacitor connected by a wire here. And if I make a zoom, I can see that in the middle I have two Josephson junctions in parallel which form a squid. More recently, it was shown around 10 years ago already that it's better to, rather than having a Transmount qubit in 2 dimensions, to put it in 3 dimensions in order to protect from environment. By doing so, people were able to get relaxation time of the order of 60 microseconds. Today it's even more, of the order of 100 microseconds. And this is in terms of T1, T2 also, up to T1. But, of course, this system is not very good for scalability. So in recent years, people have tried to come back from Transmount in 3D back to Transmount in 2D, and especially this work from the Princeton group has shown that it's possible to get a very nice Transmount with T1 up to 360 microseconds, which we call the tantalum Transmount. And the main work of this group was to understand that the origin of the relaxation problem is coming from the interface between the tantalum and the substrate. Okay, so if I'm trying to summarize, we have big advantages to Transmount qubit. First advantage is to have long coherence time. The second advantage is that it is relatively easy to fabricate because we have only one Josephson junction, and this Josephson junction controls linearly the energy, the transition energy of the system. The big disadvantage of Transmount qubits is the following, is that you have low anharmonicity. It means that the distance between the level is very close to an harmonic oscillator, and thus this brings problems of frequency crowding, slow gates, and if you want, there is an intrinsic limit to the fidelity of a Transmount qubit. So what I'm going to show you today is a superconducting flux qubit. So you see here the loop of a superconducting flux qubit. So it's a superconducting loop intersected by 1, 2, 3, 4 Josephson junctions, among which one is smaller than the other by a factor alpha. So this system has also long coherence time. I'm going to try to show you why we have long coherence time. But it has a very high anharmonicity, which means that it's a real two-level system. We can apply fast gate, and it should have a very high fidelity. The problem is, of course, you have never something which is free, so it's much more difficult to fabricate superconducting flux qubit because the gap or the energy of the qubit is exponentially dependent on the parameter of the junctions, and especially exponentially dependent on the ratio alpha between the small junction and the big junction. The second problem of the superconducting flux qubit is that it has indeed long coherence time, but only at one optimal point at half a flux quantum. So let's make a very brief introduction to flux qubit. So here you see an FM micrograph of a flux qubit, okay? And if I represent it as a circuit, you have 4 junctions on a loop. So if I'm writing the potential energy of the system, it is the sum of the energy of each of the junctions. Okay, but I'm on a loop, and thus there is the flux reading the loop. And since we have a Faraday law, we should have a relationship between the different phase and the flux reading the loop, which is given by this. So in order to show you why it's a qubit, I'm going to present you, to give you a visualization of the potential in the case, in more simple case, where we consider only 3 junctions, 2 big and 1 smaller. In that case, the potential, and I'm going to position myself exactly at phi0/2, where the potential we will see is degenerate. So in that case, the potential energy of the system can be written as a sum of cosinus plus alpha cosinus phi1 plus phi2. which I can represent like that. Okay? And you can see that along this line, there are two degenerate minima. And these two degenerate minima, which appear here, correspond to, they have opposite phases, which means that they have opposite direction of current. So one of the minima corresponds to a current flowing in the loop on the counterclockwise, and one represents a current flowing in the loop clockwise. And it's possible to give an analytical formula to give you the value of the persistent current flowing in the loop. It's given by this formula where U is a Chebyshev polynomial of the second kind. Of course, when you have a degenerate system, automatically quantum mechanics tells you that you will have a tunneling term between the two degenerate states, which will be given by delta, the tunneling rate, and you will have symmetric and antisymmetric superposition. So the problem is, how do you solve Schrödinger equation? So in order to do that, you have to consider the second part of the Schrödinger equation, the kinetic part of the Schrödinger equation. And indeed, the kinetic part of the Schrödinger equation is a little bit more complex than its potential part. You have to consider and to take into account the capacitance of each of the Josephson junction, the capacitance between each of the islands to the ground, and the geometrical capacitance between each of the islands. So to do that, okay, so first of all, we can write this term, and we can calculate with COMSOL these capacitance terms, and that's what we have done. And once you have done that, you can diagonalize your Hamiltonian, which is composed by this kinetic part plus the potential part. So if you do that, you solve the Schrödinger equation, and you see that indeed close to half a flux quantum, you have a very nice two-level system where the third level is very far, around 50 gigahertz away. The second thing that we can do is to, if you want, it's a macroscopic spin, what I'm showing you here. So the second thing that we can do is we can look at the difference between the first excited state and the ground state, and we get this energy spectroscopy, where you can see that the spectroscopy of the flux qubit is defined by two parameters. The first parameter is what we have spoken about, which is the tunneling rate, delta, and the second part is the slope of this curve, which is fixed by the persistent current of the qubit. So I need to precise here that flux qubit is very sensitive to a magnetic field. In order to show you how much it is sensitive to magnetic field, I would like to compare the electron spin sensitivity to the flux qubit sensitivity. You see that there is almost more than 5 orders of magnitude difference. So between 2.8 megahertz per Gauss to 500 gigahertz per Gauss. So this means that if you have any small noise here, the L energy of the qubit will change by a lot. And thus, it means that flux qubit in this region will have bad coherence time. The only point where we can expect to have long coherence time is exactly at phi 0 over 2, where the flux qubit is immune at first order against flux noise. Okay, so flux qubit exists already since more than 20 years. And to make a very short state of the art is difficult, but I'm going to show you that the initial paper, so in the initial paper, the coherence time were of the order of 10 nanoseconds. A few years later, it was understood that it's better to work exactly at the optimal point. And you see that the echo time was reaching something like 1.5 to microseconds. Basically, what you can say about flux qubit is that in general, T1 is comprised between 0.5 to 4 microseconds, and also T2. Except one outstanding example, which was fabricated around 10 years ago by the group of MIT, the group of Will Oliver, where flux qubit with T1 of the order of 10 microseconds, T2 of the order of 20 microseconds was measured. So the reason for this non-reproducibility was due at that time to the complex circuitry that was needed in order to measure a flux qubit. So the idea would be, let's try to simplify this. That's exactly what I did a long time ago already when I was in postdoc. And by putting a series of flux qubits inside of a three-dimensional cavity in the same idea, with the same, along the same ideas as what was done with Transmount. And indeed, what we got at that time is a large improvement, especially in terms of T1, but also in T2. And you see that by changing the value of alpha, I could change the gap of the qubit. More recently, in 2016, the group of Will Oliver has proposed to put in parallel to the flux qubit two big capacitors. By doing so, he is able to reduce the sensitivity of the flux qubit to flux noise, and also to increase by a lot the relaxation time of the qubit, up to 90 microseconds. The problem of this is that this is also the price, and the price was an harmonicity strongly reduced almost to a level of a transmount. Okay, so if I'm trying to coming back to this result in 3D cavity, you see that by varying alpha, I could change the gap of the qubit between 2.7 to 15 gigahertz. And you see that the T1 were relatively high, but there was a lot of non-reproducibility in this T1. The T1 was varying between around 2 to 5 microseconds to 20 microseconds. It was not really reproducible. So the second question is about scalability. Scalability of three-dimensional cavities, we all know that it's a question. So I'm going to present you our last results. So I'm going to try to convince you that we managed to solve this problem. Okay, so what I'm going to present you is flux qubit in two-dimensional coplanar waveguide resonators. We considered 3 different samples. The first sample was fabricated on an intrinsic high resistivity silicon. The second and third sample were fabricated on a high resistivity silicon covered by a thermally ground silicon oxide 5 nanometer layer. So this is the typical coplanar waveguide. So you see that on a coplanar waveguide, we connect galvanically a series of qubits. I don't know if you see them, but we have 11 qubits on the line. Okay? Each of the qubits is connected galvanically to the central conductor of the coplanar waveguide. So a critical element which needs to be stressed here is the new technique that we developed in the lab in terms of fabrication. Because in order to control the gap of the flux qubit, we will need to have a very high quality of our e-beam lithography. I'm going to give you an example. We fabricate the flux qubit, half of them were fabricated with this kind of constriction, which is a 30 or 20 nanometer width constriction. Okay? So this technique consists of, rather than using a simple 2-layer Dalla technique, we are going to use what we call the 3-layer technique, where we put in sandwich CISA, which is a resist, which is an e-beam resist, a layer of 50 to 60 nanometer of germanium, and below that, a spacer of MAE. So the first step is e-beam lithography. Then we make a reactive ion etching in order to transform the germanium layer as a mask. Then we can clean with oxygen hashing and make a 2-angle evaporation at low temperature and well-controlled temperature. So by doing so, we have enhanced the accuracy and the reproducibility, since, for example, the germanium mask is very rigid and does not move, The second point is that by doing low temperature evaporation, we control the size of the aluminum grains, and we control the oxidation of the junction. So finally, another advantage of this system is that we are able to clean for a very long time the undercut region, so that to be sure that no more e-beam resist is there. So once we have the sample, we put it in our dilution fridge when it works, and then have to introduce the sample inside of a coil, which is itself included into a superconducting shield with a cryoperm shield. What is important to show you here is that in order to apply a field, we need to push a current so that we use a very good voltage source and a very well thermalized at room temperature resistance in order to have a good source of current. So, of course, the OPX of quantum machine controls everything and controls the microwave resonator, the microwave source for resonator, microwave source for qubit, spectrum analyzer, oscilloscope, VNA, and here you see an optical table showing you IQ mixers, switch, variable attenuators, digitizer, well, amplifier before the digitizer of the OPX. Okay, so once we have put our sample inside, the first things we are looking for is for an anti-crossing between the qubit and the resonator. Okay, so this anti-crossing is manifested as a change, an abrupt change of the resonance frequency of the resonator. So this happens at different values of magnetic field because each of the qubit has a different size. Once we have done that, we can make the spectroscopy of the qubit, and from that extract the persistent current of the qubit and the gap of the qubit. So here, for example, we do that. We get 298 nanoampere for qubit before, and a gap of 5.18 gigahertz. We do exactly the same for the second qubit, the qubit B6 that I have shown you already. So you see that it appears at a different value. This is because it has a different size. And once again, we make the spectroscopy, extract from this the persistent current, and extract from this the gap. You see that the two gaps are very, very close. So now, if we do that for each of our samples, so we have 3 samples, and on each sample, we have something like 11 qubits. So we can represent the persistent current versus the gap. Okay? So in red, you see the qubits on sample A, the sample which is on intrinsic silicon. In green, you see the qubits on sample B, and in blue, you see the qubit on sample C. Okay? So first of all, you see that there is colored region. This colored region corresponds to an analysis that we make on the normal distribution along the axis defined by principal component analysis. And what you see also is that there are dashed lines. These dashed lines correspond to simulation where we vary the value of alpha by plus minus 5%. So from this comparison between this colored region and dashed line, you see that they are more or less well aligned. This means that the origin of the dispersion of the qubit energy is due to variation of alpha, which is usually much smaller than 5%. So the different qubits were designed with different values of alpha, and thus they are at different values of gap, but you see the spread is of the order of 0.6, 0.7 gigahertz. Once we have done that, we analyze the coherence properties of the qubit, and that's the big news, if you want. So this is the first qubit before. So from that, we extract T1, T2, T2 echo. We do the same for qubit B6. We extract the same T2 echo, the same T1, and more or less the same T2R. And now we plot all the relaxation rates for the same sample. So in red, I represent the intrinsic silicon sample. So you see that even if we manage to control, yes, perfect. Even if we manage to control the energy or the gap of the qubit, we see still that in terms of relaxation rate, we have very big changes between qubits. Okay? So in black are represented the Purcell effect. So of course, qubit with different energy will have different Purcell rate. So we need to take this into account. So we took that into account, but still, you see that we have good qubits of the order of 30 kilohertz, while we have others which have 1 megahertz relaxation time. Now let's move to the case of sample B and sample C in green and in blue, where we fabricated the same kind of device, but now on a very thin layer of 5 nanometer silicon oxide. This is the situation. So you see that we can still try to look out for a Purcell effect, but the Purcell effect is very negligible. And you see that basically, between different samples, we have more or less the same gamma 1. Another point which is important is to pay attention to the fact that these gamma 1 are good, around 50 kilohertz, but less good than relaxation rate, the best qubit on intrinsic silicon. Okay, to finalize, I would like to speak about the pure dephasing rate. So away from the optimal point, as I've mentioned already, we have a lot of flux noise, and the flux noise will dominate the dephasing rate. So, and once again, I remind you, the electron spin sensitivity 2.8 megahertz per Gauss, while the flux qubit sensitivity is 200 to 500 gigahertz per Gauss. And in fact, it's possible to have an analytical formula which connects between the rate, the pure dephasing rate, and the amplitude of the flux noise. Okay, so what we do, we just match the data in green with the theory. From this, we extract the value of the flux noise. So we get a flux noise of 1.12 micro-phi 0. It's a very low flux noise. We do this for all of the samples. So first of all, you see that they have more or less all the same flux noise. Secondly, it's a very low flux noise, 1.2 micro-phi 0. Thirdly, it's independent on the sample type. And finally, it's also independent of the presence or not of a constriction. I remind you, there was a constriction on half of the qubit. The one with the star are qubit with constriction. So the constriction does not affect the flux noise. And finally, we look at the pure dephasing rate exactly at the optimal point where we are immune to flux noise. So what can be the origin of this dephasing? Well, I said that the flux qubit is immune to flux noise at first order, but we should also consider maybe second order effects. So that's what we did, and we represent this in gray. Okay, so you see that sometimes it's a little, depends, but it's not very dominant. Another element which is important is that we are now putting flux qubit inside of a resonator. So the resonator may have photon fluctuation, occupation, thermal occupation of photons inside of the resonator. And since the resonator is coupled to the flux qubit, this influences also the flux qubit resonance energy. So we take this into account and represent this in black. Yet, if we choose properly the qubit, it shouldn't be a problem. So from where is coming the remaining dephasing rate of flux qubit? Well, in fact, we don't know. But we can propose a solution. We can propose a theory, a possibility. And the idea is that this would be the critical current noise, or if you want, some of electron which would enter inside of the insulator and modify the Andreev bond states, and thus, as a consequence, will modify the value of EJ, of the critical current of the junction. Okay, that's it for the experiment. Let's now speak about future perspective. In fact, one of the perspectives is to be able to fabricate now tunable flux qubit, where the gap can be tuned. And in fact, it's not anymore a perspective because we did that. Okay, so we added to we replaced one of the junction by a squid, by a very asymmetric squid. You can see here, this one. And once again, we put a lot of flux qubit on the resonator and analyze the data. And indeed, we see that it's possible to control the gap of the flux qubit on a range of around 3 gigahertz. The second point which is interesting and which does not figure here is that it has a long coherence time. So we managed to keep the coherence time of the qubit almost the same. And this is summarized in this work. Another very interesting thing that we can do with the tools that I've shown you is, of course, what I have shown you at the introduction. So you remember one of the qubits there was half of the qubits that were built with a constriction of 20 nanometer. So the idea is now to use this constriction and to align this constriction with a bismuth donor inside of the wafer, implanted at a distance of around 20 nanometer. Now, we have here a current which flows of the order of 300 nanoampere. So it should be able to couple strongly to the impurity, to the electron spin of this impurity. If we are able to do that, we are able to do the project. Of course, these bismuth impurities, they have a very, very long coherence time of the order of seconds, so it would change completely the game. Yes, I forgot to mention that we are doing that with our friend from Melbourne University who are doing the implantation for us. So that, but we can do a lot of things, other things with this good flux qubit. So the flux qubit can couple to spins, but also to thermomechanical resonators or to others. So, conclusion. I hope that I have convinced you that I have shown you a series of flux qubits with reproducible gaps. I hope that I have convinced you that we can get reproducible long relaxation times on substrate with a silicon oxide layer of 5 nanometer. We have a very low flux noise, and thus this allows us to couple very strongly to interesting spins. And the pure dephasing rate is typically of the order of 20 to 30 microseconds. All of this is summarized in that recent paper put on the archive. So we foresee that there would be a very nice application for building a hybrid quantum system. And I would like to thank you first, and to show you the team of QNano, this is our nickname, and the people that participate especially to this project, T.Kai Chang, a PhD student, and Tamir Cohen and Itamar Rotzman. Thank you for listening.